All right, folks, it looks like the time has come. It is 12:01 this Wednesday afternoon. Good afternoon, folks. Welcome to the Lunchtime Discovery Series. It's good to be with you again for another edition of our program, brought to you by the North Carolina Office of Environmental Education and us here at the North Carolina Museum of Natural Sciences. I am your host, Chris Smith. I work for the North Carolina Museum of Natural Sciences, and I am here to bring you this fantastic show every single week, or at least most Wednesdays at noon. We gather right here around the glow of our YouTube channel in order to hear from interesting people who are doing smart and interesting things out there in the world of science and nature, conservation and education, and even more. Of course, this month being the month of April, April has in it an oh-so-special holiday, and in fact, a day that I learned might actually be the most celebrated holiday planet-wide, and that is, of course, April 22nd, Earth Day. Apparently, something like 1 billion people celebrate Earth Day all around the world. And so if you're going to have a big celebration like that, you might as well go ahead and stretch it out across an entire month. And that's what we've done here at the Lunchtime Discovery Series. So all month long, we've been hearing from just great people who are doing some really cool and interesting stuff out there, helping us learn more and understand more about the world in which we live. And of course, today, we're going to do just that as well. So everybody, I want to introduce you to today's guest speaker, who's going to be taking us on a tour of Western North Carolina's most interesting features, the rocks. I know you're excited for it. Today we have with us a senior geologist with the North Carolina Geological Survey. It's Bart Cattanach. Hi, Bart.
Hey, good afternoon, Chris.
Thanks for being here with us today.
Thank you to the museum and for the Office of Environmental Education and Public Affairs for having me.
Bart, if you think about Earth Day, do you actually consider it Earth like dirt and mineral and rock on Earth Day?
I do, and part of what I wanted to say is that I am very excited to be here before Earth Day, because when you think about it, you can't really get more basic than the rocks in a lot of instances. So
I think that's the best perspective to have on it.
Yeah.
I'll turn it over to you. I'm excited for your presentation.
All right, let me crank it up here. Share my screen. Hopefully everyone can see that now.
Looks good.
So yes, my name is Bart Cattanach. I work with the North Carolina Geological Survey, and like Chris said, we are very excited to be here before Earth Day, because the rocks, they're the basis for a lot of different things. They control the soil that develops. They control where we find mineral deposits, why streams flow where they do, why groundwater flows where it does. It explains oceans, why there are oceans where there are volcanoes, earthquakes, and geology. It creates opportunities and hazards that help to shape how life develops on the planet. Western North Carolina geology, excuse me, is a broad subject. And so we have to sort of condense what we want to discuss a little bit today, but I'm hoping to give you an understanding of the structure and composition of the rocks in the Western North Carolina, as well as the tectonic history, how they got to be the way they are. And I work out of the Asheville Regional Office. I'm primarily a geologic field mapper, and we analyze we respond to the public's inquiries, and we produce basic scientific information. Our duty station is everything from I-77 west in the state, and that's what I'm going to focus on today. And you can see on this side that the mission of the North Carolina Geological Survey is to provide unbiased, accurate, applied earth science information to address societal needs. So we are your geological survey. So anyone out there who has questions, you're looking for geological resources, please feel free to contact us, because we'll always do our best to try to make sure you have the information you need going forward. We're excited because 2023 is the North Carolina Geological Survey's 200th anniversary. We were founded in 1823, which makes us the oldest state geological survey. And I believe you talked to one of my coworkers, Heather Hanna, a couple of weeks ago. And so yeah, we're pushing that, and we have activities planned all year for helping to celebrate the 200 years. So before we move into talking about the rocks directly, I want to take 2 slides to discuss some basic earth science concepts, which a lot of you are probably familiar with, but I want to get us on the same page before we start discussing the rocks. And you can see a cutaway of the earth here, and you can think about the internal divisions of the earth in a couple of different ways. You can think of them as physical, whether or not something is solid. Is it semi-solid? Is it liquid? You can also think of something as looking at the chemistry of it, where you have a core of iron, nickel, metal moving into the mantle of mostly iron, magnesium silicates. And then on the outer surface of the earth, you have much lighter silicates. If you're looking, you can see that the crust and the upper part of the mantle actually make up this solid lithosphere. And the surface of the earth is broken up into lithospheric plates. And there's a map over here showing most of the major plates. And these plates are free to move around. They're created, they're destroyed, and they can move around the surface. And it's this action we know as plate tectonics that provides the engine for creating the geology that we see. And so it's important to sort of understand and have some basic principles in mind as we go through the talk. This lower map down here, or lower figure, shows different types of plate tectonic boundaries. And the basic one I want to talk about is called the divergent margin. And you can see 2 arrows here. That means these plates are being pushed apart or pulled apart. And this is a mid-ocean ridge where you're creating new oceanic crust in that ocean basin. So you're making these plates larger, and they're moving away from that divergent boundary. We know the Earth is not getting appreciably larger, so for creating crust, we have to destroy it somewhere, and that happens at these convergent margins. And in our example here, we're pushing oceanic crust. It's running into continental crust, and it's being subducted. That subduction causes earthquakes along the margin, and it also creates volcanic activity, all things which we've had in the past here in Western North Carolina. The third type of plate boundary is known as a transform margin, and that is where 2 plates just slide past one another. So the best example of that, everyone's probably heard of it, is the San Andreas Fault in Western North America, where the Pacific plate is sliding north past the North American plate. So the other basic geology side I want to talk about just is pretty much referring to the density of crustal materials. We have an example of continental crust rock here on the left, granite. It has a density of 2.7 grams per cubic centimeter. And then we have basalt on the right. It is denser than the continental crust. So as these solid, as these materials rest atop the mantle on the surface, this oceanic crust is going to ride lower. And we all know gravity pulls everything down. So water that falls anywhere on the planet is going to eventually make its way out to the oceanic crust. And this is why we have ocean basins where they are. And we'll see some of the interaction between the continental crust and the mantle here in the next few slides. I've still got 2 more slides before we actually talk about rocks, but want to talk about the physiography of Western North Carolina. The inset map here shows the southern Appalachian Mountains, and we start over here in the east. You're at the coastal plain, you move into the Piedmont province, into the Blue Ridge, and then finally out into the Valley and Ridge and Appalachian Plateau. So in North Carolina, we have the Blue Ridge and the Piedmont. You can see the Valley and Ridge in Tennessee. It's defined by these really elongated valleys and ridges with more resistant bedrock. As you move down into the Blue Ridge, as you move to the southeast, you get into a higher elevation, higher relief, more rugged topography that you can clearly see from the photo here. And as you continue to move east, you move down into the lower elevation, gently rolling section of the state we refer to as the Piedmont. The transition zone between the Blue Ridge and Piedmont we refer to as the Blue Ridge Escarpment. And it is a very rugged area. You can see there's just a diagram of where the escarpment is here. And the reason it's called the Blue Ridge is that as European settlers encroached westward, this was the first large ridge that they would see. You'd get to the escarpment and it became known as the Blue Ridge because of the hazy blue appearance. And this name eventually became synonymous not with just the escarpment, but with the entire portion of the southern Appalachian Mountains. I showed this. This is the opposite view. If we had settled the country from west to east, perhaps we'd have the Blue Valley instead of the Blue Ridge. So now I want to actually transition and start talking about the rocks themselves. This is a excerpt from our 1985 State Geologic map, and you can see there are a lot of different units on here. There's just too much on this map to be able to talk about in the time that we have today. So we have to simplify things a little bit. And we can think about the basic building blocks that make up the rocks that you just saw on that map. And we're going to go very simple today, and we're going to talk about basement rocks and cover rocks. And the basement rocks shown in gray, you can see on this the map of Western North Carolina. Cover rocks shown in brown. The brown cover rocks are resting on top of continental crusts. So this gray basement is continental cover just because of where it's deposited. And the rocks we have in pink we refer to as oceanic cover because they are predominantly deposited upon oceanic crust, which is here represented by the black line. As we move further to the east, we get to this other light gray material. This is also oceanic crust, but it has a different affinity, and we'll get to that in a moment. And then we get to the real strangers once you get to the Kings Mountain and Charlotte area. These are very different rocks than what we have in the rest of Western North Carolina. I'm going to show this diagram again, but I want to introduce just a couple of quick ideas. This is a tectonic history, and it shows what the plates were doing throughout the Paleozoic. You can see one GA, this is 1 billion years ago. We have collision. You can see these arrows pointing towards one another. So you had convergent margin. So you're creating a large landmass. As you fast forward through time, we rift apart this landmass, and then we bring a series of tectonic elements. They collide with this ancient North American margin here on the left to produce what we have today. And we're going to go through these one by one, but I do want you to think about the dynamic nature of plate tectonics. It's operated for a long time on Earth, and it really explains why we have the rocks we have. So the first thing I'm going to discuss is the basement rocks. These are the oldest rocks, and they began structurally as the lowest rocks in Western North Carolina. Most of the next slides will have some common elements. One, I've got a geologic map showing what element we're referring to. And then I have this time scale. The green arrow refers to the rocks we're discussing on each particular slide. So these rocks, the basement rocks, were formed between 1.3 and 1 billion years ago in a series of mountain building events. Geologists have a fancy term, orogeny, for what is essentially a mountain building event. I have a picture showing a typical basement rock. There are many different types of rock, but here's a picture of these really high-grade gneisses. It's a very high-grade metamorphic rock, and you can see they're clearly cross-cut by these much younger igneous rocks. And in the lower left, I have a basic tectonic diagram explaining what was happening during the time that these rocks were created. So a period of 1.3 to 1 billion years ago was a period of continental collisions. And we have on the left what is essentially proto-North America. And on the right, we have what is known as Amazonia, which is you can find in South America now. Well, these two were colliding to produce a large mountain chain that ended around, that collisional event ended around 1 billion years ago. I've got these green dots here because there are much older pieces of material, older minerals that have been discovered in the basement. And so we know that there were rocks of this age that have been eroded and recycled that are in our current basement in Western North Carolina. So let's move over. We're going to fast forward now about 250 million years. And you can see our arrow has gone forward, and we're now looking at something called failed rifting. And you can look at our tectonic diagram here, and you can see the arrows are pointing apart. So that old supercontinent Rodinia that formed 1 billion years ago is beginning to be pulled apart. We don't really understand why, but for whatever reason, this rifting did not succeed in creating an ocean basin, but it did create basins in continental crust where you had sediments as well as volcanic material deposited in these basement basins. And these rocks actually form the Grandfather Mountain Formation. They're shown in green over here. These are some of North Carolina's most iconic rocks, and they look different from everything around them because they are different. They were formed in a different time period and have had a different tectonic history than the surrounding basement and cover rocks. So let's fast forward a little bit more in time. You can see we've gone to around 600 million years ago, and we get to successful rifting. We look at our tectonic diagram here. Rodinia has been rifted apart, and the western portion of it is something called Laurentia, and you can think of it as proto-North America. And on this Laurentian margin, where we rifted these this continental crust, we get additional sediments being deposited. And most of these sediments are very coarse-grained, very immature, because they are being deposited from the mountains which are right beside them. This is a picture of a conglomerate. So you can see the large quartz clasts in here. The Ocoee supergroup is our term for them. They're shown in green on this particular diagram, and you can see that they make up a large portion of Western North Carolina. So these are continental cover rocks deposited on top of continental crust. We're going to fast forward just a little bit more to the end of the rifting here with our green arrow. And what's happened is this margin, which was active rifting, has now transformed into a more passive place. And you can see the rocks that were deposited during this passive margin time period. They include the Chilhowie Group, Shady Formation, Rome Shale. You see them in green here around Hot Springs. And then you can see similar rocks, maybe even younger, the Hiawassee River and Mineral Bluff groups down here in southwestern North Carolina. And the cool thing about these rocks is once you go transition from that active rifting to a passive drift margin, you can deposit rocks over a much wider area. Before I move there, this is a picture of Linville Gorge, and these are some Chilhowie quartzites on Shortoff Mountain in McDowell and Burke counties. And these are really good sandstones. Table Rock is also Chilhowie, and then you move to Hawksbill, which is Grandfather Mountain Formation. But it makes for some very dramatic scenery. Now, I just showed this to illustrate where these rocks were deposited on a regional scale. The brown rocks, the Ocoee Supergroup Rift rocks, were deposited locally in North Carolina, Tennessee, Georgia, and Alabama. But as the rift margin developed and became more mature, you were able to deposit rocks all the way along the southern Appalachian margin. So everything shown in green are equivalents of those Geohazards, Shady, and Rome formations. Let's talk a little bit about the oceanic cover now. Oceanic cover is shown in pink, so it makes up the majority of rocks that we see in western North Carolina, and they're shown in pink down here on our diagram. We call them oceanic cover because they're predominantly deposited upon oceanic crust, even though in this diagram you can see the rocks are actually very similar. The sediments are very similar to some of these rocks that are being deposited on the continental basin, with the important difference in that they are incorporating a lot of basaltic volcanic material, and eventually they would incorporate pieces of the oceanic crust that they were deposited on. All of the green rocks that you see here are considered to be mafic. Those are very rich in iron and magnesium, and the rocks in purple are considered to be ultramafic, so even lower silica than what you have in most of these green rocks. And the depositional model for these is you've rifted apart, you're looking at a rifted continental margin, and you are shedding lots of sediment off of this margin in large, you can think of them as debris flow or large flow deposits that have come off the continent and rest out here on this ocean basin. And within those, you get lots of circulating fluids and basaltic volcanics that are interbedded with these rocks. So if you look at the continental cover rocks, you very rarely see, only in a few instances do you see these basaltic volcanics, but in the oceanic cover rocks, you have lots of these mafic and ultramafic rocks. This is just a diagram showing subduction. After these have been deposited, as oceanic crust is subducted underneath continental crust, you get little slivers of that oceanic crust that end up in the oceanic cover rocks. So now we're moving away from rocks that were deposited strictly or have influence that were strictly from the Proto-North American or Laurentia, these basement rocks here, and we're bringing in sediment from not only the west, but from the east. This is a cutout of one of the tectonic cartoons that I showed earlier, and this circle represents an ocean basin where these continental deposits, these oceanic cover deposits were being deposited. So after a orogenic event, you were eroding material from Proto-North America, but you were also bringing in material from something called Gondwana, which you can think of roughly as a Proto-Africa. So even though these rocks are very similar, they have input from two different, very different locations. And as we go down to our final tectonic element, these are what we call peri-Gondwanan arcs. And these rocks have nothing in common with the basements in Proto-North America. They're actually pieces of Gondwana that were left behind during some of the Paleozoic mountain building. And we have the Kings Mountain belt here, and then we have the Charlotte terrain over here. So it's a piece of these materials. It will get shoved up onto North America. And I'll show you that here in our next slide. Here's our tectonic diagram again. We'll go through everything one more time, showing continental collision 1 billion years ago, forming the supercontinent Rodinia. We are going to successful rifting of Rodinia. And over here on the west, we have Proto-North America with sediment being deposited. You also have sediment being deposited, shown in pink, in this ocean basin. And you can see that the polarity for the tectonics has changed. We're no longer rifting, and things are starting to move together in the Paleozoic. So around 450 million years ago, we had our first major ocean building event. And it's where this oceanic crust, probably volcanic activity out here, as well as the sediments, is connected. It's actually a part of a large mountain building event, and it is accreted to this proto-North America to become part of Western North Carolina as we know today. And I show little bits of the oceanic crust in black to show how things get incorporated onto our continental margin. But if you look off here to the east, you can see we have a couple of other tectonic elements coming in. And so if we fast forward, we have our second major mountain building event, and that is when you have the sediments, the oceanic cover rocks, and the cat square terrain, and you have the Charlotte and Kings Mountain belts, which are formed and cemented onto ancestral North America. Now, I've got these circles here to show the X shows movement away, and the little dot shows movement towards. So if you're imagining what's happening, it's not just a head-on collision, but there's actually some transform motion going on as well, so that you get oblique collision, and the western portion of North America was actually moving relatively northwards compared to these other continents, the peri-Gondwanan continents that were coming in. Now, if you look back, we have the largest, or I guess most influential mountain building element coming in right now, and it's in green, and it's known as Gondwana. It's that proto-Africa. And when Gondwana collides with ancestral North America, you get this large series of old previous mountain building events, and everything is being shoved several hundred kilometers to the west over this ancient North American basement. This resulted in the creation of the supercontinent Pangaea at the end of the Paleozoic, where essentially one continent, everything is together at the same time. And if you look at our diagram again, you can see an east or a west to east shift from our mountain building episode. So we've got the first one is further to the west. The second one took place a little further east. And then the third main one, part of the Alleghanian orogeny, was even farther east. We see evidence of that if we look at the minerals in the rocks of Western North Carolina. These minerals that I have shown over here are considered to be metamorphic indicator minerals. So you've got lower temperatures and pressures on top with higher temperatures and pressures down below, going from chlorite to a mineral known as hyperstein. This is an isograd map, and it essentially just separates areas where you find different kinds of minerals. So if we go up here in northwestern North Carolina, near Hot Springs, we're at chlorite grade. Very little metamorphism. But as you start moving to the southeast, you get this core of very high grade metamorphic rocks, with hyperstein being present in the rocks here. And so this core, shown by these high temperature, high pressure minerals, represents that tectonic core. This is where the main portion of that first orogenic event is located in Western North Carolina. As you start moving east, you start dropping down metamorphic grade, and then you start picking up again. You're going down from kyanite, then you start picking up to sillimanite, and this Si2, which is, we refer, it's second sillimanite, which is the presence of the mineral sillimanite without white mica. You've had metamorphic reactions to remove white mica from these rocks. And this is the core for that second mountain building event that we refer to as the Neo-Akkadian or Akkadian orogenic event. As you keep moving east, you can see you start dropping down a metamorphic grade again. You find sylvanite, and then you find kyanite, and then around Kings Mountain, things start to pick back up again. This is the edge of what we're talking about, but you get into sylvanite, and as you move further to the east, this is the core of that third mountain building event known as the Alleghanian. So if you live in the eastern Piedmont, the rocks have a very different history than the rocks in far western North Carolina, even though some of them may be similar in terms of their initial composition. We not only have metamorphism, but we're creating igneous bodies during these orogenic events. And some of western North Carolina's best scenery is represented by some of these bodies. You have Stone Mountain, which is located here in Wilkes County. You have the Henderson Gneiss. This is the largest igneous body or pluton in the southeast, and it takes up a lot of Henderson County. This particular spot is of Hickory Nut Gorge, and this is a metamorphosed granitic body. We have Looking Glass Pluton in Transylvania County, and we have the economically important deposits of spruce pine, which are also plutonic bodies created during these large Paleozoic mountain building events. Just to show a few examples and to give you the scope of some of these plutonic bodies, this is from one of the spruce pine bodies, the Hoodow Mine. This is a large granitic pegmatite, and you can see this dark colored group of rocks here. This is actually a piece of the Oceanic Coverrocks that were not completely assimilated into those spruce pine pegmatite rocks. We call these xenoliths. They're strange rocks that you find. They're essentially leftover rocks that weren't completely melted when the plutonic body was intruded. So you've got these large scale plutons, but you also have smaller scale. This is only about 2 feet across, and you can see we have metamorphosed sediments. These are part of our oceanic cover rocks on either side of that, but we have this igneous body intruded into these sediments. And these are shown by these hatched patterns here. We can't map all of these. They're too small, but this is where you find them primarily, and there are literally tens of thousands of these bodies scattered throughout our oceanic cover rocks. We also have faulting, and I can't cover all of deformation that occurred during the Paleozoic in western North Carolina, but we've got these major faults that separate some of these large tectonic elements. You've got the Hayesville Fault, the Holland Mountain, Chattahoochee, Burnsville Fault, Gossan Lead Fault, the Brevard Fault Zone, which runs all the way from Virginia to Alabama, the Brindle Creek Fault, which separates the Cat Square terrain from our other proto-North American oceanic cover rocks. And then when we get into the Peri-Gondwanan terrains, we've got the Kings Mountain Shear Zone. And we've represented this. This is kind of a cartoon, but it does a good job of incorporating all of the elements that we've talked about so far. This is a cross-section from Charlotte down here in the southeast, going all the way to the Knoxville area in the northwest. So you're going from Charlotte here to Knoxville here, and you can see the different types of rocks that underlie western North Carolina. So we've got the North American basement here, but we also, just north of Asheville, we have it exposed at the surface along with some of our continental rift rocks. And these rocks, it's important to think of, like during that last major mountain building event, the Alleghanian event, all of these rocks were pushed from here in the east far to the west. And so you can sort of what we call retro deform. If you start pulling these rocks out, pulling the faults out, you can bring this basement down to where it's part of this ancient North American crust. You can pull your drift rocks back to where they're on top of the continental crust, and the oceanic rocks would get pulled back as well as we know our strangers here, they would be much further. They were deposited or formed much further to what we consider geographic east nowadays. You can also see the faults that separate some of these features. We see the folding that has affected these rocks, and these little sort of solid color blobs represent some of those igneous plutons that intrude the rocks of Western North Carolina. What I just showed you was the geologic history, the tectonic history through the end of the Paleozoic period. But we know things didn't stop in the Paleozoic and Pangea. We had the tectonic regime shifted, and we started to pull Pangea apart. And that is shown by this tectonic diagram here. And this is the exact same diagram I used earlier, but I've changed the name. So this is really North America this time. We've created a new margin that we think of as the Mid-Atlantic Ridge, and we have the Atlantic Ocean. We have failed rift basins in North Carolina, and they are shown in green. You've got the Deep River Basin here, the Dan River, and the very small Yadkin-Davie Basin here, where you have sediments, mostly Triassic age sediments, that were deposited in these basins as things began to pull apart during the Mesozoic. You can see our green arrow has fast forward in time, and you can see the current tectonic setting, where this red is the young Mid-Atlantic Ridge, and these colors cool off. The oceanic crust is older the farther away you get from the Mid-Atlantic Ridge, where it's pulled apart these continents. Although we don't have Triassic basins or sediments deposited in Western North Carolina, we have plenty of evidence to attest to that Mesozoic rifting. One of the lines of evidence are these large red lines here that we refer to as diabase dikes. These are very steeply dipping igneous bodies that cross-cut all of the old rocks that were deposited or formed during the Paleozoic. And we also have lineaments that you can detect looking at LIDAR, which is light detection and ranging. You can think of it as radar, but using light. And these lineaments, in many cases, are parallel to these actual igneous bodies. The smallest, or the furthest west we found one of these igneous bodies is located right about here in Rutherford County, and it's only a foot across, but it has the exact same orientation as its larger brothers and sisters, and there are literally hundreds of these as you go east into the Piedmont. But it has the same orientation as these lineaments that you can see, and it also matches up very well with a lot of the fractures. These blue lines are actual, they represent thousands of measurements where we've gone out and taken structural data, and these are essentially cracks in the surface. They're brittle features, and many of them are parallel to these dikes and lineaments. And if you look down here, we have a slightly different orientation in a lot of our fractures, and they line up well with brittle faults, where you have fault breccia that we believe was related to the Mesozoic rifting as well. It's important, I just want to mention here that we're pulling apart everything in Western North Carolina, but the actual topography may be much younger. So even though we have very older rocks, the mountains themselves may be considerably younger and caused by some form of topographic rejuvenation, maybe within the last 30 million years or so. The mechanism behind that is unclear, but there are several different lines of evidence which make us think that we have old rocks but relatively young mountains. I just want to show you some of what some of these rocks look like here in the Western Blue Ridge. You've got these really old, older than 1 billion year old gneisses. You have failed rift igneous bodies that intrude into those gneisses. This is a picture of Max Patch granodiorite. This is a large igneous body that underlies Max Patch in Madison County. And here is the same version of this rock, but you can see it's now very finely layered. Some of that Paleozoic mountain building event has faulted this rock and deformed it. So even though these rocks look very different, they started out exactly the same. And here's an example of some of our continental cover sediments in the western portion of the state. And you can see they're very coarse. This is a good one because it shows this coarse conglomerate on the left, and it's overlain by a very fine-grained shale on the right. And this contact between the two was originally horizontal, but during the Paleozoic, it has been shifted, it's been folded, and now that contact is vertical. So we're referring to this gray area here of our basement and continental cover rocks. So we look at some of the rocks as we move to the east. These are some of our central Blue Ridge rocks, which are part of our oceanic cover. Not only do we have lots of sandstones and schists, but we have these ultramafic rocks as well. If you've heard of olivine or altered ultramafic rock, which can produce asbestiform minerals as well as talc. This is an example of dark rock, as you probably have guessed. This is a mafic rock, similar in composition to the oceanic crust. There's just more examples of that. I think this is a good example of the interlayering of the sediments we see, where this is a coarser sandstone, and our finer grained shales, when they get metamorphosed, they have more micas in them. And so you can see the difference in the rock today. And you also have this partially melted rock in a lot of these, in a lot of samples, where these things were metamorphosed to such a high grade they began to actually melt. We also have cool minerals like garnet. This is about a regular pin size, and garnet is a metamorphic mineral that can grow quite large in places during some of these mountain building events. So we move out to the Cat Square terrain, named for the community of Cat Square. We have some of these same oceanic sediments. You can see the folding in them. And this is a granitic rock that it was also really sheared by Paleozoic deformation. And then finally, we get to the Kings Mountain and Charlotte belts, and you've got these peri-Gondwanan sediments. Here you can see some which are standing almost completely on end. And these are holding up some of the more notable features in the Kings Mountain zone. This is the Crowder's Mountain. This is actually the pinnacle here. And then Crowder's Mountains further to the south. And you also have a lot of igneous rocks associated with this blue Charlotte terrain. I want to just talk about the minerals that we've mined in western North Carolina. These are the ones that we currently produce. You can see we've produced a lot of other minerals previously, and some of these minerals could be produced again as economic conditions change. This is a picture of spruce pine, which is important economically for those granitic bodies that were intruded into the oceanic cover rocks. And most of what's being produced here is feldspar quartz, including high purity quartz, which is well sought after for the electronics and technology industries. And it used to be, it still does produce mica, but it used to be, this was sort of the original commodity for western North Carolina, was mica, because Native Americans mined it thousands of years ago to use for ornamentation and ritual purposes. And you can find ancient tools in the softer portions of these, the weather portions of these granitic bodies. I want to look at just where these commodities are distributed, just to give you an idea, put them in context to that basement cover rock that we were talking about. And you can see most of them are located in our cover rocks. And some of them, like marble, are located in very specific areas based on the geology that you see. So these are all, this is a kind of a busy diagram because it shows where things have been mined. These are not active mines right now, but if we take away the feldspar and mica mining and just show them by these hatch patterns, and we do the same with gold, which you can see here. You can get a better distribution of the underlying rocks, and you can see how over here this limestone marble belt corresponds to those youngest cover rocks in southwestern North Carolina. You can see how these are marble deposits which are associated with Brevard Fault Zone, and you can also see in the Kings Mountain belts lithium, which is one of those commodities which is now in higher demand. We mined lithium in North Carolina for over 50 years, and they're trying to reopen some of the mines in the Gaston-Lincoln County area. I wanted to do a quick shout out to crushed stone and gravel because it's the unsung hero of geology. You can't have cement, you can't have building, you can't have roads without some form of crushed stone or gravel. And the good thing about crushed stone and gravel is you can use a lot of different rocks to have a quarry to produce that particular mineral. You can see or a particular commodity. There's not really a correlation between the rock type and our crushed stone commodities. It's just essentially where can you find the best material locally, because it gets expensive when you start moving rocks around. And the final economic side I want to talk about is corundum. It's the mineral corundum represents both rubies and sapphires. And you can see that corundum, olivine, vermiculite, these are all associated mostly with our ultramafic rocks, those bits of oceanic crust that were incorporated into the cover rocks during the Paleozoic orogenic events. You don't see those mafic rocks out here in the continental cover. I want to do quickly, and I'm running out of time, just quickly talk about some of the geohazards we have in Western North Carolina. Earthquakes. We don't have very many large earthquakes in North Carolina. You can see this is a map of epicenters, and you can see the East Tennessee seismic zone here is much more active. And anywhere along an active plate boundary, you have larger, frequent earthquakes. In North Carolina, luckily, our earthquakes are usually very minor, with the notable exception of the 2020 Sparta earthquake, which is 5.1 magnitude. And this is just some pictures of the damage in the Sparta earthquake. And the Sparta was great because it gave us a lot of information on how some of these earthquakes may form. This is the only recorded earth rupture due to an earthquake in the eastern United States. Out west, you have ruptures with the larger earthquakes all the time. We'd never had it in the east until the 2020 Sparta quake. We have something called acid-producing rock. This is essentially, some of these cover rocks can have a lot of sulfides in them. And as they break down, they can produce a lot of extra hydrogen that will reduce your pH. And you can see here, you've got an outcrop of acidic rock here. It's coming out and it's actually eating into some of the concrete along the roadway. If you have enough of this acidic rock and it goes directly into a stream, it can impact aquatic life. We have rockslides and falls. These are just simply areas where rocks have slid, in mass, or they've fallen, is a single blocks or a series of blocks. This is an example from Broad River Fire Department in Buncombe County. Doesn't look too bad from the outside, but if a truck or people had been there when it happened, it would have been devastating. Same thing from Spruce Pine. Not too bad from the outside, but would have killed someone if it had occurred during business hours. And there is a large economic impact to our transportation network, where these large rock sides, this is one from Pigeon River Gorge, it shut down 2 lanes of Interstate 40, or pretty much all of Interstate 40 for a long time, and it took over $10 million to repair. Here's a large truck per scale. Here's just another example of a slide that happened within the last 10 years. And then finally, I want to do just a mention of debris flows, because these are probably our most devastating form of geologic hazard. And it's where you can get material that will mobilize at what we call an initiation zone, and it will head downhill collecting material as it goes. And these can actually go for thousands of feet to miles. And someone who's living down in a valley area may not be aware that there's a hazard lurking up above. So I know it's 12:50. I just want to talk about what we do really quickly. Why do we do what we do? Well, we get basic information on geologic hazards such as the landslides, radon, acid rock, asbestos minerals, arsenic. All of the data that we collect from our geologic mapping is useful for site-specific purposes. We are a public organization, so anyone from a private landowner to a company to other government agencies can get the maps and the information that we produce. And we identify possible mineral resources, and we're working towards working with the USGS to create a seamless national map in a digital format. So I think I'm going to stop talking there and just open the floor up to see if anyone has any questions.
All right. Fascinating stuff. Thank you, Bart.
You're welcome. Thank you for having me. There's a lot to cover. There's a lot to see.
Oh, yeah. You only had a billion years worth of stuff to talk about today. A billion years of stuff. Well, I do have some questions for you and several that have come in from the chat. So I'm going to go straight to our viewers and see what they're thinking about. And I'll see if I can't just take these in order as the way they came. A good one here. Troy wants to know, or Troy says, there are extremely huge black rocks along the Cherahalla Skyway. There were no small pieces of this rock, only super large boulders. What is this black rock, and do you know anything about it?
I would have to see the rock, and it's also very difficult to identify a rock strictly from a photo. So I don't know right off, but if Troy can send us an email, send me an email, and with the approximate location, I can probably give him a fairly good idea about what makes that rock up.
All right, there you go. And there were a handful of questions about the mineral resources, stuff that gets mined. So one was, what mineral is a part of the copper deposits near Copper Hill?
So Copper Hill, those are related to what if you heard, I used some weasel words on the continental Coverrocks when I said these very rarely have this mafic magma, these intrusions associated with them. But places like Fontana, Hazel Creek, Copper Hill, Ducktown in southwestern or southeastern Tennessee, they are associated with these very localized mafic magmas. And so they're mostly sulfides with associated copper.
Okay. And then the folks in the Environmental Education Office were curious about hiddenite, where they've seen it's labeled the fourth rarest gem in the world. What factors in Western North Carolina geology led to its development?
So, hiddenite is associated with some of those igneous bodies during the Paleozoic. They're associated with very coarse-grained igneous material, and I guess the composition of it is what makes it a little more special. Differentiates it. It's actually, I think, a spodumene, which is a type of more common mineral, but it's got impurities in it that give it a little different color. And so, but it is associated with those igneous intrusions into the cover rock, the oceanic cover rock.
So that puts them that was the 460 million year mark.
Those are probably younger intrusions. Yeah, so you've got 3 of those mountain building events, and the igneous intrusions that are affecting the hiddenite is probably the middle version of that. Those, what we call Akkadian, Neo-Akkadian, anywhere from 360 to 340 million years. There's a big error bar on some of these things. So,
okay, gotcha. All right, Michael had the next question. Do you compare your geological specimens from North Carolina with other areas of North America?
Sometimes I'm not sure I completely understand the question, but we always look to other places that might have similar types of rocks. So, if you were to look at like sort of the protolith of a lot of our oceanic cover rocks here, may compare well with some of the sediments which are being deposited off of the west coast of North America today. If those rocks were to be metamorphosed and shoved down a subduction zone, they might end up very similar to our oceanic cover rocks.
Yeah, I guess similarly, or maybe this sort of relates. If you're looking at a continental cover rock in North Carolina and you're trying to figure out the extent of it, or if it's in fact, or I guess, how do you know that it's, say, a cover rock versus something that's much older or a part of the deeper crust?
So the Grenville crust, that basement rocks that we're referring to, it's actually undergone a series of those are usually very high grade gneisses, and they have lost, in many cases, they've actually or we don't know what the protolith was. They're so high grade, we don't know what they were before they were metamorphosed. That is not the case with our continental cover rocks in Western North Carolina. You can still identify a lot of relict depositional features like bedding planes and channelized deposits that you can't see in, or at least reliably see in the higher grade basement rocks.
Okay, I got you. And David says here that they may have felt that Sparta earthquake all the way in Apex.
Absolutely, yes. And you can go. The USGS runs a great site where you can go and look, and they have what they're called felt maps, and you can look up. You can do a search for pretty much any earthquake, click on it, and it will tell you where people reported feeling it. But Apex is, a lot of people in the Raleigh area did feel that 2020 earthquake.
I'm guessing the day of and maybe the aftermath of that 2020 earthquake was probably a busy day for you.
It was, especially the aftermath. And we spent a lot of time out there. A lot of researchers, besides ourselves, we had people from North Carolina State, UNC, the USGS, many organizations sort of teamed up to try to understand what had happened. And we still don't have a conclusive answer as to why that particular area failed when it did. But we, at least with that ground rupture, we at least have a lot more to go on than we did before.
And you said it was the only ground rupture in the East.
In the East, that has been recorded history. We've had other larger earthquakes, like there was the Mineral Virginia quake that a lot of people in North Carolina felt and damaged the Washington Monument and the National Cathedral. But there was no ground rupture associated with that. And usually 5.1 is actually a fairly small earthquake to have ground rupture at all. This turned out to be a fairly shallowly centered earthquake. But being able to map that rupture and have an idea about the relative motion will hopefully help people understand, like, hey, why did this happen? What are the risks going forward? Because the rocks that we saw around Sparta, we've seen similar rocks and textures all over Western North Carolina. We do still feel that, these are much less, these happen much less frequently than they do along active plate margins, though.
Okay, that's fascinating. I guess one more superlative for North Carolina.
That's right.
All right, last question for you here. Randy Bechtel wants to know, what is your favorite part of North Carolina geology and favorite part of being a geologist?
So my favorite part of being a geologist is being out in the field. And it's not only the rocks. I love the rocks, but it's meeting new people every day. We interact with a lot of people in a lot of different capacities. And it's very fun. It mixes the job up a lot. And as far as the geology itself, I love those old ductile fault zones that we have in Western North Carolina.
I love that. It's great to have people working in state government who love their jobs and are good at it.
Well, yeah, we certainly, I can't speak for all of us, but I think most of us in Geological Survey, we are committed and we really like what we do. I just ran out of time. I had a whole series of slides showing, what we do on a daily basis, but maybe one of my colleagues, I know Dr. David Cordy, has expressed possible interest in going to a deeper dive on some of the geohazards.
Yeah, the EE folks mentioned that we might have a speaker coming up who's going to talk about some of that stuff. So I encourage folks to stay tuned, watch this space, because we're going to keep talking about this because it's relevant. It's cool. It's interesting.
Absolutely. And we're happy to help out. If you have questions, you can Google North Carolina Geological Survey. Our contact information is on there. Thanks for this opportunity.
Yeah, sounds great. I know that folks are going to take advantage of that and the resources that are available. Bart, thanks for being part of the Lunchtime Discovery Series today. We really appreciate your time.
Thank you.
And everybody, thanks for tuning in to this edition. Make sure that you're following the museum and the Office of Environmental Education on social media, or make sure you stay plugged into our websites, naturalsciences.org and eenorthcarolina.org. There you can get information about all of the events and upcoming programs and lectures that we've got here at the museum and at the Office of Environmental Education, particularly for this series as well, so you know what's going on and what speakers are coming up soon, because the lineups just stay good. We keep meeting really great people, and they keep sharing just all kinds of great insights with us in terms of what's happening in North Carolina and beyond. So I hope I'll see you all again here real soon at the Lunchtime Discovery Series. Until then, though, happy Earth Day, everybody. Take care, stay safe. We'll see you again soon. Bye, everybody.